pleasure to be here. Very excited to have the opportunity to talk to you. I want to start off by apologizing to everybody who asked me, will you be at Q2B and can we meet? And I said no. Turns out I was wrong. So I'm really excited to be here. I want to tell you about some of the work that we're doing at Oak Ridge National Laboratory in quantum science and innovation. And we actually have a very broad portfolio, and I'll only touch on parts of it because what I'm really going to focus on is segueing off of what Charlie just told you about in terms of the NQI and talk about one of the DOE's NQI centers, the Quantum Science Center, where I'm the directive. Now, if you don't know, Oak Ridge National Laboratory is one of the Department of Energy's federally funded research and development centers. It is nestled in the hills of Tennessee. You can see the panoramic view here. It has a long history of doing research in material science, all the way back to the graphite reactor, which was the second demonstration of nuclear fusion back in World War II. In particular, that materials processing expertise has transferred over the last 75 to 80 years to now development of new types of medical isotopes at the HIFER reactor, the development of a spallation neutron source for characterizing new types of materials, and the development of advanced manufacturing facilities. But what really counts, from my perspective, at the intersection of quantum technology and what we're doing at Oak Ridge is that we have home to the world's fastest supercomputer at the moment, a system known as Frontier. It's the world's first exaflop system. It's also a demonstration of how you can use computing in order to support the types of material science research that's going on at the laboratory. Now, the Quantum Science Center is intended to help us take that laboratory into the future. In particular, we're focused on three technical goals: accelerating quantum information processing, predicting new physical and chemical behaviors with quantum computing, and enabling exploration of the previously unmeasurable using quantum sensors. And I want to talk about each of those goals and what's motivating us and how we're approaching that. Now, in the first case, to accelerate quantum information processing, we know that currently noise and errors limit our ability to scale up the types of materials that we have on hand today. There are protocols for fault tolerance and mitigating the effects of noise, but these are in fact relatively costly overheads to have to assume. We can, however, create new types of quantum materials that intrinsically encode these types of fault tolerance protocols into the materials themselves. And at Oak Ridge, as part of the Quantum Science Center, we're exploring this class of materials known as topological quantum materials. And the neat thing about this is that we can already synthesize and characterize and fabricate these materials. What our goal is within the center is to demonstrate that we can control them, and control them in a way that can then be used for quantum information processing and ultimately for new types of qubits. In predicting new physical and chemical behaviors, simulation is an ongoing development at Oak Ridge, including using the high-performance computing systems. Scaling up our conventional methods, though, ultimately reach a challenge when it comes to quantum mechanical models, either in terms of the amount of memory that's required to represent those models or the amount of time it takes to reason with them. We know that quantum computers can offer an efficient representation of those models, but the trick is being able to devise the algorithms that actually simulate the models and get out the results that you're looking for. Again, coming from Oak Ridge, one of our goals is to understand nature, especially materials, chemistry, high-energy physics. So we're building these new types of platforms and algorithms that can simulate those scientific problems. In enabling exploration of previously unmeasurable, here we are facing this challenge that the sensitivity and selectivity of conventional sensors are limited by the physics themselves. For example, if we're looking for the Majorana fermions that are actually one of the sources of these new ways of encoding quantum information, we have to create new types of sensors that can get below the current noise levels. Similarly, if we're looking for exotic forms of matter, such as dark matter, we have to come up with new techniques that can be used for measuring those types of signals. So in this case, we are building and calibrating new types of quantum sensors that are targeted specifically towards detecting topological quasiparticles and for axionic dark matter. And the goal of the center then is to be able to deploy those systems in a fashion that could transition into larger searches for these types of systems. Now, when you summarize all three of these goals together, what we're really doing at Oak Ridge is trying to overcome key roadblocks in the scaling of quantum technologies. Whether it's developing new types of materials, new types of algorithms, or new types of sensors, all of these are intended to focus on the long-term goal that we're going to need much larger systems than we have access to today. Now, in the demonstrating of controlled interactions in these topological states, we're actually taking advantage of many of the DOE's national user facilities, including the CNMS at Oak Ridge, which allows us to fabricate new types of materials, the spallation neutron source I was talking about earlier, and the Oak Ridge Leadership Computing Facility, which we use for numerical simulation. But we're at the point now where we're actually able to create models of these materials, synthesize them in the laboratory, and then start to transition them into proto-devices. So for example, this anti-dot down here actually puts together a topological insulator and a superconductor in a unique geometry in which we believe we can create some of these Majorana fermions that we're looking for. Now, ultimately, we need to be able to control these particles in a way that can demonstrate that, in fact, they are storing quantum information. And so this is what's known as verifying the non-abelian statistics of those particles. So that's our goal in the long term for the center. Now, as part of that, we're actually putting in place a new facility known as the Translational Research Capability. It has over 93,000 square feet. Most of this is focused on laboratory space, including space for demonstrating new types of quantum experiments. The materials that we're talking about here, as well as the methods of characterizing their interfaces. We're hoping this will be done by the end of 23. In the second area, looking at the development of new types of algorithms and platforms, it's actually a mixture of hardware development, including ions, photons, superconducting transmons, as well as neutral atoms, and then the development of the algorithms that would run on those systems. Now, we're using conventional, if you will, quantum computers that are available today to demonstrate digital quantum simulation. But our real effort here is taking these experimental systems, tuning their design so they can actually provide efficient representations of the problems that we most want to solve, which includes things like understanding how chemical reactions are occurring or where these exotic particles arise within quantum materials. Now, part of this is supported by what we call the Quantum Computing User Program. This is supported by the Department of Energy separately from the center, and it provides access to commercial quantum computing systems. And you can see three of the types of systems we have here from IBM, Rigetti, and Quantinuum. Providing access to those systems, we're actually able for our internal researchers to develop their ideas and test the technologies and get feedback on what works and what doesn't. But this program has actually been expanded to include people from outside of Oak Ridge as well. So as a user program, it's merit-based. If you write a great proposal, you can actually get access to these same types of technologies. We then evaluate how well people are progressing in their development of programs to run on quantum computers and use that as guidance on where are the hot topics right now to be pursued. Finally, in the third area, we're developing and demonstrating these systems to measure exceptionally weak signals. Some of this is actually creating exotic quantum structures where, for example, in this case, we have a diamond-tipped probe that is traversing across the surface of this particular device in order to try and identify where some of the defects are in the device and better understand its physics. We're also able to create single photon sources embedded in quantum dots that can then be put into the materials which we want to understand at their interfaces and used as a source of detection or sensing in that particular apparatus. So there's a lot of work right now going in the development of these materials, but we have some very interesting work with our collaborators at Fermilab in trying to create cryogenic environments in which we can isolate these types of quantum signals from, say, other background sources of noise. And in particular, can we create those types of cryogenic environments to now become detectors for signals such as cosmic particles. So this is a really exciting area of research where our search for quantum materials is actually intersecting with our development of quantum sensors. Now let me just give you an example of how the center works and how it brings all of these things together. So in one of our technology pathways for developing topologically protected quantum information, we have a class of class of materials called quantum spin liquids. A great example of this is ruthenium chloride. Now, we've recently shown that we can take ruthenium chloride over to the spallation neutron source, and we can detect entanglement in the material itself. So what I'm saying here is there is a crystal about this size, it's about black. If you cool it down low enough, so less than 1 Kelvin, and put it in a high enough magnetic field, you are literally holding entanglement in your hand, because the ground state of that material is in fact entangled, and that's what our characterization techniques have shown. Now, admittedly, if you're holding it in your hand at that point, your hand's frozen and you've had to, seek medical attention. But the point is that that is what the exciting possibility of this new material provides. At the same time, we're using access to quantum computers to simulate the Hamiltonian that describes this, the Kitaev-Heisenberg Hamiltonian, and from that, developing quantum simulation methods that can provide feedback on how that material should behave in the presence of different external perturbations, and ultimately how we can control it to create new types of devices. So one example of how that happens is we can demonstrate thermal transport in these quantum spin liquids in a way that shifts their quantum states. If we can control that shift in their quantum state, that gives rise to new types of devices like interferometers, where now this material whose ground state is entangled has a temperature gradient applied to it and begins to interfere with itself. And so for us, this is a great step forward in the demonstration of how to control this new class of materials. So the center itself is not just located at Oak Ridge. It is in fact a partnership of 17 different institutions. You can see all of their logos here, but I will call out, for example, Los Alamos National Laboratory, Purdue University, and Fermilab as our major research partners. Microsoft, IBM, and Cold Quanta, though I think they may have changed their name, are actually our primary industry partners here, and then we have many other universities supporting us as well. So in total, there's probably about 250 people in the center. We're working geographically distributed around the country, but we're lined across these 3 research themes that I've been talking about. Now, the centers themselves are not just about doing research. They're also about transitioning these ideas out into the larger ecosystem, which I think Q2B's audience represents. And I'll give you 3 examples of how we're doing this. With Microsoft, we actually are working on these candidate topological materials, understanding better about how we need to design and test them before we can transition them off into something that may need to be addressed from a manufacturing or fabrication concern. We're also working heavily on the quantum intermediate representation that hosts a lot of the software interfaces. With Cold Quanta, we're working on the application of Bose-Einstein condensates, quantum matter that can be used as a quantum sensor. In addition, we can actually use that quantum matter as a proxy for other Hamiltonians, other quantum systems that we want to simulate. So now we're looking at the intersection of how quantum algorithms and quantum sensing can create new types of platforms. And with them, we've actually created a new interface to their experimental atom interferometry. And then with IBM, we're working on the development of these scientific discovery applications. How do I take a material simulation problem and scale it up to these large number of qubits that I know I'm going to need in order to become competitive with our conventional high-performance computing systems? So this is a really exciting area because it actually pushes on new methods for encoding information in the quantum state and mitigating the errors that we know will arise. That intersects very well with our other interest in how to encode information topologically across different materials and then ensure that we can lower the overheads in the long run for scaling up to fault-tolerant computation. Now, I said I was going to talk about Quantum Science Center, and I did mostly, but I want to mention that the other parts at Oak Ridge that intersect with the idea of computing, sensing, and networking in the quantum information space. So we have a very strong quantum material science program. In addition to the Quantum Science Center, we have a quantum information science section. This is where the heart of our information theorists and experimentalists reside. We also have the Quantum Computing Institute, which runs the quantum computing user program I was talking about. If any of you have ever seen the QCI newsletter, that's where it's coming from right there. And then in addition, we have our national user facilities, which have a mandate to support the national research agenda, and that includes its intersection with the quantum research portfolio. So in total, there's probably just under 100 people at Oak Ridge working full-time on quantum information topics and helping transition these ideas out into technology. So with that, let me just summarize by saying that I feel like the Quantum Science Center is playing an important role right now within the national landscape, becoming a focal point, not just for a new research direction, but also for how those ideas can support the broader ecosystem. And I will look forward to taking any questions if we have time for that. Thank you.
Thank you, Travis. We do have time for one question, if anyone has a question for Travis. Okay.
Bob.
Great talk, Travis. Can you just briefly go over how you interface with the other DOE quantum research centers?
Great, yeah, great question. So there are 5 DOE NQI centers. Quantum Science Center is one of those. We have a joint council where all 5 centers meet together. We also have joint activities that we work together on. Some of those will be things like joint workshops. We've worked with SQMS, the other center that's led by Fermilab, on joint workshop for quantum algorithms for simulation that we were just talking about. Sylvia in the back there, she and I are actually supposed to get together in a couple weeks to talk about a joint summer school. So the centers all have very unique research agendas, but they have common concerns when it comes to things like workforce development or technical exchange, user facilities, these types of things. So we do coordinate.